7.2 is the division properties of exponents. 7.1 was the multiplication ones. What happens with different types of multiplication? What happens to all the exponents? So, similar to that, division properties, it's what happens when the bases are being divided. What happens to the exponents? So, learning target. This is still part of learning target 7a, which is I can simplify expressions using the properties of exponents, so any property. So, if you remember 7.1, something like c to the fourth times c to the third. What this meant was that c to the fourth was just a shortcut for c multiplied by itself 4 times, and then c to the third is essentially the same thing. And so I have 4 of these c's being multiplied to each other, multiplied to another set of c's, 3 of these that are multiplied to each other, and then if we wanted to simplify all of these, there are 7. So c to the 7th power, right? The shortcut that we wanted was c to the 7th. We got this, was that when we have the case of the same bases being multiplied to each other, then we add the exponents 4 plus 3 to get that 7. So that was for multiplication. When we have the same base and we see a division problem, like an example A, c to the 11th over c to the 8th, if I were to expand both of those exponents, on the top we have 11 c's being multiplied to one another, and then in the denominator we have 8 c's being multiplied to the denominator. Now, when you're dividing, c divided by c is just 1, right? So they cancel. So any pairs of c's that I see, one in the numerator, one in the denominator, they just cancel like that. And ultimately, we have 8 cancellations. We cancel what we can, and with the stuff that we can't cancel, we have c to the third left over in the numerator, c to the third over 1, or which is just c to the third. Now, again, we want to have a shortcut. So we ultimately know that c to the 11th over c to the 8th is simplified to c to the third. What we notice is when you have the same base, you just need to subtract the exponents from the biggest to the smallest. And that's it. So try example B on your own. I know there are 2 variables, but you have to treat those separately with its respective exponents. Pause the video and then try it, and I'll kind of go through it together. So we have g cubed times h to the 5th over g times h squared. This g right here has an exponent of 1. So you want to make sure to keep that in mind. To simplify the g's only, we have g cubed over g to the first, and so we subtract the exponents 3 minus 1, and so I have g to the power of 2. And then looking at the h's, h to the 5th divided by h squared, you subtract the exponents, and so you have h cubed. And so my simplified expression is g squared times h cubed. So that was an example of what to do when you have the same bases being divided by one another. If you need to rewind the video, please go ahead and do that now that you've copied down the notes, and you can just watch it again. Otherwise, I'm going to go on to the second one, where we have, in this example, so like a fraction in a parentheses, and that whole fraction is being raised to an exponent. So I know it looks a little funky here, but it's 3/5 all raised to the 4th power. What you do here is this exponent, in some sense, gets distributed, kind of like a over b raised to the m power. This m is distributed to every single base in that fraction. So in this first example a, we have 3/5 raised to the 4th. This exponent 4 goes to that numerator, and it also goes to the denominator. So we can rewrite this as 3 to the 4th power over 5 to the 4th power. And then if you can evaluate it, like here, then evaluate it. 3 to the 4th is 81. 5 to the 4th is 625. And so that's my final simplified answer here. In example B, we want to make sure, again, so we have 3 times p cubed, all divided by 7, all of that raised to the second power. Now, I know the 3 and the p are squished together and it looks like they're the same thing, but you do want to keep in mind that 3 is a separate base from p, and which is a separate base from 7. So I'm just underlining all 3 bases here, just so I know that this squared, or this exponent 2, it needs to go to all 3 spaces here. Now, this then can be written in the numerator. I have 3 squared, and p raised to the third raised to the second. If you remember from 7.1, you multiply those exponents to get p to the sixth, all divided by 7 squared because of that exponent. And then evaluate any of the numbers. So 3 squared is 9. P to the sixth can't be simplified anymore. 7 squared is 49. And so this is my final simplified expression. Again, if you after you copy that down, if you just need to watch that again, see what happened, pause the video, rewind it to the second part, and then just watch it one time through. So we've looked at lots of different types of exponents. This third part for today is what about a zero? Anything raised to the 0 power. So weirdly, anything to the 0 power is equal to 1. Let's think about that for a little bit. If I have, let's say, a to the 5th divided by a to the 5th, okay? Using my shortcut from before, I know that I have to subtract these 2 exponents, so I get a to the 0 power, right? Now let's kind of backtrack a little bit. If I were to expand a to the 5th, I have a times itself 5 times in the numerator and in the denominator. And remember, this was a shortcut for like anytime they cancel. So in this case, all 5 of the a's cancel. And so when they cancel, it's not equal to 0, but it's equal to 1. And so we just saw that a to the 5th over a to the 5th, which is the same thing as a to the 0. And that just means all the a's disappeared, and so that just equals 1 because everything canceled. So that's kind of the proof as to why the exponent of 0 evaluates to 1. Now let's look at example A here. So this is where it gets a little bit crazy. I have a negative 4n squared q to the 5th r squared, all divided by 9n cubed q squared r, all of that raised to the second power. So again, remember, this exponent 2 is going to distribute to every single base, and I'm going to underline all the bases just so you can see more clearly. Just want to make sure that you recognize that the 4 is separated from all the variables, the 9 is separated from all the variables. So if I were to distribute that squared, it even affects this negative, right? Because if you think about a negative number squared, a negative fraction squared will make it positive. So what I have now is, once I distribute that exponent 2 to all the bases, this is the expression that I have, right? Again, the exponents kind of multiply here because n to the power of 2 raised to another power of 2, I multiply. Q to the power of 5 raised to another power of 2, I multiply those exponents. Now the 4 squared and the 9 squared, those can be evaluated to 16 over 81, just like that. Now a question is like, how do I know when I'm done? As long as you have if you have a variable that's being repeated, like you see n and in the numerator and n in the denominator again, like that's not simplified. So I want to just make sure that all my n's are like together. So here, if you notice, n to the 4th over n to the 6th, you would have to subtract this. Now, I said bigger minus smaller earlier. Wherever the bigger exponent is, that's where the leftovers will be. So here, my bigger exponent for n is in the denominator. My q, the bigger exponent, is in the numerator. My r, bigger exponent is in the numerator. So this is kind of what I mean. So I mean that, so 16 in the numerator, and then since my 16 over 81, I'm just going to kind of leave it like that. And since for my n variable, the exponent 6 is in the denominator, so 6 minus 4 is 2. That 2 means it's going to be in the denominator. Q to the 10th minus, or divided by q to the 4th, so I subtract the exponent, so I have q to the 6th, but since the bigger one is in the numerator, I leave it in the numerator. Same with r squared. So I know that was a little bit confusing. Now I know this is simplified because I only have one q, one r, and one n. So that is my most simplified expression. So that was a little crazy. Let's try example B. Example B, I have x to the 5th times y to the 0. Okay, so here's the thing. Anytime I see y to the 0, that pretty much just kind of like cancels because it's just 1, right? So then I have x to the 5th divided by x cubed, same base. I subtract the exponents, and since the 5 is bigger in the numerator, it's going to be left over in the numerator like that. X squared divided by 1, but you really don't even need the divided by 1, so x squared is my final expression. I know that one was a little confusing. You might have to pause and rewind that. So why don't you go ahead and do that if you need to. Otherwise, I'm going to move on to the fourth thing, which is the negative exponents. Mrs. Joe told me to tell you a joke just in case you're bored, but I will not do that. The fourth thing is, what if my exponent is negative? Which is very much a possibility. So when you have a negative exponent, so if you look at this, a to the power of negative n, what happens is that the whole base and exponent all together go to the other part of the fraction. So meaning a to the power of negative n is really over 1. So this essentially goes down to the denominator. And so it's not so much the reciprocal, but it goes to its denominator. So kind of let's look at example A here. For A, 2 to the negative 4th is written as, so in my denominator, this 2 to the positive 4th, right? So as it moves to its denominator, it becomes positive. But then now there's nothing in the numerator. There's always something in the numerator. It's a 1, right? So 1 over 2 to the 4th, we can evaluate that to 1/16. Now for B, if I have 1 over j to the negative 4th and the negative exponent is in the denominator, then it can become positive just by moving that whole thing to the numerator. So j to the positive 4th power, and then that's it. That 1, so some of you might be asking, like, what happened to that 1? It's kind of being multiplied to the j to the power of 4th, which is why you no longer really need that 1. So, you know, in the last page, there are 4 kind of crazy examples of applying all the properties that we just did. It might be better just to kind of see those examples being played out, because I'm sure a lot of this just kind of went over our heads a little bit. So let's move on to an example, one of the fun examples on the next page. Alright, fun example A. I have n to the negative 5th, p to the 4th in the numerator, all divided by r to the negative 2 power. Now notice that there aren't any multiple variables, but the reason why this is not simplified yet is because of these negative exponents. So simplified means positive exponents. This is a negative exponent, so that means it needs to go to the other part of the fraction from the numerator to the denominator in order to be positive. Same with this r to the negative 2nd power. This in the denominator needs to move up to the numerator. P to the positive 4th is already positive, so I'm just going to leave that there. And so if I were to rewrite this whole thing, it would be p to the 4th power, r now to the positive 2 power in the numerator, and in the denominator n to the 5th power. Looking at my exponents, they're all positive. Each variable is only showing up once, so this is simplified. Part B, we have to look at these a little bit separately. So if you imagine here, so 5 over negative 20, we can simplify that. R to the negative third time, or divided by R squared. Got to simplify that. T to the fourth divided by T to the seventh. We got to simplify that. Now U to the negative 5, since that's a negative exponent, we have to simplify that. 5 over negative 20 simplifies to 1 over negative 4. Okay, I'm just going to make kind of a long fraction just because I don't know what else is going to happen. R to the negative 3 minus 2. The bigger number is the 2. So if I do 2 minus negative 3, that is R to the 5th power. Since it is in the denominator, my evaluation is going to be in the denominator. T to the power of 4 divided by T to the 7th. Again, since 7 is in the denominator, my evaluation will remain in the denominator. U to the negative 5th just needs to be positive, so I need to bring that up to the numerator. That joins the 1, so 1 times U to the power of 5. If you choose to, you can just get rid of the 1 times, and so you have U to the 5th all divided by negative 4 R to the 5th T cubed. And so that is what's simplified. Why don't you try C and D on your own? All I'm going to do is going to provide the simplified expression and then not really explain it, but for you to just jump into the practice. I know this was a long video and it was a lot of stuff, a lot of new properties, but really I think it'll just make more sense as we practice a little more. So have a discussion with one another as you try these things. So here are the most simplified versions of examples C and D. For C, there wasn't, honestly, there wasn't much work to show. Maybe just kind of take a look and see like how I was able to get that. For D, I simplified everything in the parentheses first, and then I distributed that exponent of 2 at the very end to all of the bases. Have a discussion with one another. If you have any questions, you can send me a quick message on Canvas or just ask me. Otherwise, you can start the practice.